This assignment is about 3 topics: indirect measurement, rescaling, scaling up or scaling down, and transforming measures. Later, we'll be applying these topics to data. But, in this assignment, we'll again be applying them to shapes and distances. And again, the goal is to develop ways to visualize things that we'll be doing later. One way to measure the height of a tall tree is to pick a point P some distance away from the tree. Then, count footsteps from P to a point A at the bottom of the tree. Next, sight from P to points A and B at the bottom and top of the tree. And, one stride length from P. Mark the point A' and B' as shown in the diagram here. The red triangle PAB should be similar to the triangle PA', B'. So, if you imagine filling the big triangle with copies of the small red triangle, then you can see why the formulas at the bottom of the screen are true. Here is another way to think about the kind of transformations that we have been investigating. Imagine 2 sets of parallel lines, like the red lines and the blue lines shown here. If both sets of lines are parallel, then distances are preserved. But, if one set of lines converge to a point, then only ratios of distances are preserved. And, this is true regardless whether it is the red lines or the blue lines that are converging. Next, let's see how parallel and converging lines look when we are thinking of transformations of data instead of transformations of trees or geometric shapes. This diagram shows 4 identical sets of data. As you can see, if we draw lines to connect matching data points, then the lines are parallel. But now, notice what happens when we subtract the value of the minimum score from each of the other scores. The red data set shows the result. Next, let's stretch the green and blue data across a larger interval. Notice that the dotted lines between the red data and the green data now converge at the blue point. And finally, let's move the data so the minimum value is at any point that we wish. And again, notice that the dotted line between the blue data and the black data or the red data will converge at a single point, which, in the case of the black data, is off the left side of the screen. Here is another example that will involve statistical data. And this time, the data will be generated by a Tinkerplot sampler. The sampler shown here generates scores for 26 students whose names are given in the first device. Then, when you click the sampler's Run button, a graph will appear automatically, showing scores from a test. Now, let's click and drag to reduce the size of these objects. And then, plot a graph of the results. Next, let's add more columns to the table. The first new column will slide all of the scores so the lowest score is 0, without changing the way the other scores are distributed. To do this, we open the Tinkerplot's function tool, and we type in a formula that subtracts the minimum score from each of the other scores. Then, if we drag these new scores down into the graph, we can see what happened to the data. Notice that the scores continue to be distributed in the same way that they were originally. But now, the lowest scores start with 0. Now, let's use the same methods to add another new column in the table. And, this time, we want to shrink the scores so that they go from 0 to 1, while still maintaining the same distribution. Next, let's add 2 sliders, and call them M, and S. The S slider will allow us to stretch or shrink the data to any size we want. And the M slider will allow us to move the data so they start at any point we choose. Here are the formulas that allow these two sliders to work for two new columns of data. The S slider stretches or shrinks the data. And the M slider moves it to any place we want. Finally, notice that all of these transformations of the data preserve the basic distribution of the data. Only the starting points and endpoints change. Now, if you return to our base exemplar, then you can run the simulation as many times as you wish and you'll still be able to rescale the data to be on any interval that you wish, while preserving the distribution of the data.